Hello, hi everybody. Uh, Welcome to our tutorial 2 on UMD implementation of using Omnet++ simulator. In the last lecture, I discussed about the different NAD files which I have defined under this folder, which is you can see there is some total 6 NAD files have been defined. Like app NAD, which is simple module, then routing NAD, it is also a simple module, and the NAD, it is also a simple module. Using the three simple module, I have make a node, which is a compound module. You can see here the multiple simple modules make this node as a compound module, and multiple node is used in the in a network, and which is named as random graph n.nad. This is our main network, which can have n number of nodes. It is a user defined parameters n, that if we give a value, then it will generate that number of nodes, and the connection among the nodes is defined by the degree of connectedness, which is here. Now you can see a degree of connectivity. So based on this value, we can expect how much our network is dense, and how much like if a degree of connectivity is 1, then it is a completely mesh network. Also I have defined one more simple module, which is network topo info, which is normally the controller. You can see here there is one controller is there. It is responsible for storing the network information, like the connection among the nodes, the weight of the link, the routing table. All these information is managed by the network controller. So these are the NAD files. The NAD part is completed now, and now let's understand the C++ part and coding of all these NAD files, because we have to so one more important thing is that we don't need to define C++ coding for compound module or a network, because these are the not active part of our network. We have to do the coding for the simple module, because simple module is responsible for basic functionality implementation of any algorithm. So you can see that we have app.cc, the definition of app NAD, and the property definition is done in that C++ file. Then we have, you can see, network topo.cc. It is also a controller. We have done this coding in C++ because it is a simple module and it is a header file. We also, you can see that there is a routing.ccc and routing.header, because routing is also a simple module, and routing is also a simple module, and so we need to define the properties. And another one is a q.ccc and q.h. This header file, this is our C++ file. You can see there. One more thing you can see here, that the packet.msg. Normally any node before moving to the C++ implementation of each of the NAD file, let's understand what is .msg message. You know that the node communicate with each other, so the packet they will send from one node to another node will carry some information. The type of information which need to be stored, which is required for our implementation, is defined in packet.msg. You can see this is the keyword for definition of packet. The packet name is itself a packet. So these are the different information which I have stored, which each packet will contain, like source address, destination address, how much it has a hop count on reaching the destination. The size of the packet is also stored in the packet itself. Traffic class, whether this defined packet is unicast traffic, multicast traffic, broadcast traffic, anycast traffic. The different type of traffic class is defined in the packet. Then broadcast on, if it is broadcast traffic, then will make it to true. Then broadcast packet number, the number of broadcast packet. Then route, the packet will contain the route information, that because in UMW at the source at the source, we have to decide its complete route. Once it is decided by our routing protocol and the routing module, that information needs to be stored in the packet, because when that packet is injected in the network, it will not change its routes, because it is a dynamic routing. It is possible that if a node is decided a certain path to a destination, and when it is traversed to that destination via the intermediate node, it may be happen that the intermediate node will change its route. It will not will as similar as it is decided at the source node. So we have to store that information, store its path in the packet, so that it is not changed by any other intermediate node. And this is the array size index. It is a temporary user defined value which needs to which is important while we are iterating to the route of the node. So all these are the definition. We can also define multiple things like multiple, that means name of the packet, different possibilities are there. So this is a very important file. So when we define this properties of a packet, the Omnet transmitter will automatically generate these two files, header file, packet, because the packet is the name of that message. The packet which we are sending is the name of the packet underscore m.h is the header file, and .c. You can see how much it is complex, because it is not written by the user. It is written by the it is automatically generated by our OM simulators. You can see how much it is complex the coding is. So it saves a lot of time of the user. Otherwise we have to manually define all of these functions and properties of the packet. So it will automatically generate. You only have to worry about what type of information you are interested to put in the packet. So this is all about packet.msg, and you don't bother about you don't need to bother about these two files, packet.ccc and packet.h. So okay, so now let's concentrate on one by one. So let me close all the NAD file, because we will start from the app.nad and app.ccc. So let me close all this file. So let's start with the app.ccc. This is our complete definition of written in the C++ coding, and in order to implement the properties of desired which we required to that file and application file. Since it is a source file, and in our cases we have make the source to generate the file regularly, like we may generate 10 packets per second, 100 packets per second, 1000 packets per second. So firstly understand what this what is our intention to define app.cc, what type of work we are interested to implement on app.nad. Firstly, it will send the traffic, it will send the packet. The packet may be, and it will define the packet class as well, like whether it is unicast or broadcast, multicast, or any cast. The definition of packet, the number of packets generated per second we need to implement. Another is the in the application.cc we will define the source address and destination of the packet randomly. Another is what we want is we want to we want it to it receives the packet from different source, because it may be a destination address as well. So it will take the information from the packet, like how much it has the hop count, how much it has the delay. So these are the different properties, and in this and as a parameter analysis we have defined two parameters. One is end-to-end delay. Whenever it will receive a packet, from the packet information it will get the information about how end-to-end delay and hop count. These are the two different parameters defined in order to analyze our results. So let's start. This is the we have to these are the files that we need to include, like map, vector, Omnet.pd is a header file that is very important, need to be included in order to define or inherit the different defined classes of the Omnet++. This is the packet, the header file of that message definition, packet._m.h. This is the string.h header file for string operation. This is the controller header file. It is network topo.h. It is basically the network controller. We need to have a communication between the network controller and our app.ccc, because this network controller stores the information of our complete network. It has the layout of the network, so all those information are stored in the that network topo.h file, the simple module, and the application module will communicate with that node for a different information. This is a standard file. Namespace standard defined is the Omnet++ namespace is included in this file. Now you can see that app.ned basically inherits publicly the C simple module. It is a class defined in the Omnet++, and that need to be inherit publicly. So let me show the hierarchy of the module available in with us. Like you can see, this simulation library. You can go refer this website for information about the hierarchy. You can see that these are the classes which is defined in the C simple module class reference object namespace on C simple module. You can see that this is the hierarchy chain. This is at the C object is at the top level and the C simple module is at the bottom level. So in the C simple module, different information, you can see that there is a constructor, destructor, assignment. These are the different functions, member functions which have been defined for message sending. This, and you can use any when you will inherit this class, you can use all of these member function whenever required. So for this I will show what type of member function I have used in our formula implementation. So let's start with the int my address. This is a variable of int type. This is nothing. It will store the information of the node index. That is, if it is node 5, then it will store the value of its value will be the 5. So app and because all the node have a app ned file, so all the these application ned will have different my address, the value of this my address. This is a number of nodes in the network. It will store that value. The packet size, what are the user defined packet size provided as input to the simulator. This is the number of packets sent by the source. It is the number of packets received by the source. This is the C module is the object. It is object. Basically we have, you can see that you have included this file, and in order to get the address of the network topo info, that is controller, we have, because it is simple module, we can use a variable which is object of type C module. So that object will refer to the network network controller module, so that they can get they can use the attributes and the different member function of that module. Is the interval time. It is nothing but it is a variable pointer to get the information about how much after how much interval a packet needs to be generated. This is the traffic type of a map is defined, and we have used the type definition so that don't need to write this one off step every time. So traffic type is defined, like what type of traffic we are using. The traffic type, this is the variable of type. Traffic type is user defined variable, user defined data type. So set traffic type is a variable of user data type, traffic type. Then is the C message is the nothing but you can see if you make the cursor here, you can see there is some information is coming. You may read for further information. This is the C message. It is object that represents events, message, job, or other entities in a simulation. So to represent package, use the C packet subclasses. So it is a message that all the packet is generated. There is a pointer is attached with that, so that you can use the different properties of that packet. Like you have already defined some like source address, destination address, hop count. You can, if you want to access these variables, you need to define the C message. There is these are the two different counters in order to count how much the packet they have sent and they have received. Since we have defined two different files, signal, not files, signal, in order to have stored the or record the our results. So we need to tell app.cc that we have defined this two, because it is defined in NAD language. So in the C++ language, we have to tell that we have defined these two statistics, two variable to record our statistics. So you can see that for this you have to use this keyword sim signal underscore t and name of that signal, like end-to-end delay signal. You can see that the name is similar to this end-to-end delay signal. Another one is the hop count signal. You can see here the hop count signal is there. So we need to define always whenever you define any signal in the NAD file in order to record some information about when the simulation is in progress, we need to tell the C++ part that we have defined this type of signal. Now this is the different member function of this simple module, which is a app constructor and is a destructor, which is you may be aware of this what is the constructor and what is a destructor. It is publicly defined. You can see this is private defined. Private, you may understand that these are all variables, and member function is not accessible to by any other module or any other compound module. They cannot access this information is make private by this app.cc. This is publicly this is protected because we need to inherit some properties, some information from this app module. So we define two different functions. You can see the virtual void initialize override, virtual void handle message. It is the input parameter, that is message, and override. You may be aware this what is virtual. This void is the return type. Override is used. I hope you may understand all these. What are the importance of using this? Well, because we are using override because since our apps class, we have defined a class of type app. So and we are inheriting publicly C simple module. So all these two functions, initialize and handle message, is already defined in our simple module class, and we are inheriting it, and we want to modify this function. So in order to modify, we need to give the override, because if we do not provide override, whatever the modification we'll do here will maybe possible that they are then maybe modified there also, so our intention may not be fulfilled. So for this to avoid any problem, that we need to tell that we are in the inherited class, we want to redefine these functions. Also, one important thing is that for every NAD definition, we always need to provide these two member function, because it is very important, because initialize is invoked when there is at the initial setup, when you are not running the simulation, you are initializing the simulation. We are doing the simulation for any variable which is defined in the private section of the class is initialized here under this member function, and this handle message member function is automatically invoked whenever the module receive any message. You can see that there is a input parameter, there is argument, sorry, not improper, this argument. Whenever a message will arrive to a module, this handle message will automatically invoke, and under this member function, whatever you make a definition of your different properties will be executed. So now let's start. Before going to next, you can see that define module app. Now we have to register this app.cc because it is a class and we are inheriting it from a simple module. We need to tell our simulator that we have defined a app class. So by registering this module with the Omnet++, so for this we have to use this keyword define underscore module, then the name of our NAD file, that is app. So this is the constructor and destructor. Now in you can see that a constructor we have generate null pointer, because generate packet is nothing but the is used for generation represent a pointer. So because at the initialization there is there is no packet, so there will no any address. So for this we make it initialized by null pointer, and at the destructor we have to delete this generate packet. So for this you can use the cancel and delete keyword. Okay, so this is our definition of member function, which is initialize. This is a function which is invoked at the when you are starting your simulation. That means when you are initializing your setup. So it is automatically invoked, and you can see that there is a different definition. This is the pointer that is pointed to the network controller. So you can see that this is a function, this is a member function which is defined in C simple module class, which is used to find the graph of is used to find the module, simple module, not the graph, simple module in our network. Because you can see that a network may have n number of node, there is a network controller. So this pointer, because we have defined it to be C module, it will point to a simple module, and this is the name of our variable. So we are defining it that we have this variable. It will find a random dot network controller. You can see that there is a, you can see that where is our network. You can see that we have a network controller here is. So it is a store. You can see the information of this. This is basically defined in random graph dot network controller. So it will, if you provide the path get module by path, so it will point to that network controller. If you give the path like random graph dot network controller, it will have the pointer to that module. Now since network control manager, the target module network manager, we have to check and cast, because it may be possible that there is no such a simple module in our network. So it will check and cast whether the simple module is available there or not. If it is not there, it will give an error. It will not crash our code. So you can see that the network topo, we have defined a network topo info and it is the pointer, the target, and point to that one, because you can see that network topo info is our C++ definition, and network topo info is nothing but a you can see it is a class. It is a class. So in order to have access of this the public part of this class, we need to define a object of that class, and which we have done here. Network topo is a class and it is the object. It is the object of our network topo info class, and that will now check and cast of the simple, because simple module is defined in NAD file, and we are interested to get the information of C++ part. So for this we are doing check and cast. Now this is a number of nodes. So this is obtained by this is a object of the network class. So this is a member function get number of nodes. You can see here there is a definition get number of nodes. Okay, you can see there is a member function. Where is the member function? This one, you can see that it is a member function we have defined whose return type is int type, and you can see its definition. You can see get number of, it returns the number of nodes in the network. So what we can say that we have defined a object of that simple module, that class, and that from that class we are getting some information. We are fetching some information from that simple module, like a number of nodes is defined in this module C++, number of nodes. That information is provided to this simple module from the network controller. Also the packet size also obtained from, it is a packet size, it is, you can see that it is defined in the network topo info network controller class. So that information is also obtained from there. Another is that what is the my address, the address of the node, it is also the of int type. So this address is obtained from the NAD file. You can see there is a NAD file. We have some value, this user defined value address of that node. That information is obtained via the PAR keyword. That it will take information from the NAD file to our C++ file. We initialize that number of packets sent to 0, packet received to 0. You can see that we have, since we have defined a map, so here you can see that we have mapped 1 with unicast, 2 with broadcast, 3 with multiclass. For whenever the value is 1, the unicast traffic will be sent. When it is value 2, is the broadcast traffic will be sent. For as of now, we are only interested with unicast, and we will see the broadcast, multicast, unicast in our upcoming videos. So also this information, like a send interval, like how much packet is sent and how much interval, is obtained from the send I time interval. Is a following parameter. You can see that there is a parameter send it whose unit is second, and it is defined as that at 0.1 second 1 packet is generated. So in the 1 second 10 packets will be generated. So that information is obtained from the NAD files. To obtain the NAD file, either you directly use the PAR, and if you have defined a pointer, then you have to give the address, like this. So also we make this two variable initialized to be 0, and this is the watch keyword is used when at the runtime, if you want to see what is the packet counter, what is my address, what is the number of passage. These are the different variables which will be changed while our simulation is going on. So at the runtime you can see using this watch keyword. So now let's start our coding. So this is a generate message. It will generate a new message whose name will be the next packet, and it schedule at is a keyword that is used to, you can see, read here, it is a self message. So that means it is a parameter that represents how much time it will generate a packet, and it will generate a packet with whose name will be next packet, whose name will be next packet. So you can see that if we provide this value to be 0.1 second, then schedule at will what will do, it will repeat itself at every 0.1 second. That means 0.1 second a packet will generate again, at 0.1 second it is a self message. The model will make a counter time, it will make a timer, and at every 0.1 second whatever the value we provide here, a new packet will be generated, and the generated packet will be this one. So and another is we have defined the sim signal for analysis purpose, for result analysis purpose. You can see that we have defined two sim signal t, and these are two different data type of this variable. Now we have to register these two signal with the Omnet++. So for doing this, we have to register signal into and delay, and register signal hopcode. These are the two different keyword used to register the signal. You can see that returns the signal ID for the given signal name. Signal names and ID are global. Signal ID of particular name get assigned at the first register signal call. Further register signal calls for the same name will return the same ID. So okay, now this is the initial this memo function is completed. Now you can see that we have what we are doing here. We are getting some information of defined parameters in our defined parameters in the private section of this class, and search a module from in the network via its path, and then we are making an object of that module, and getting some in calling some member function of that module, and after that we have initializing our different parameters via this zero value, or maybe unicast, broadcast. This is the definition of our map function, and so on. And it is also a generate map, because at the initialize member function we have to generate a packet. So when it will generate a packet, the handle message will be invoked, because when the handle packet will receive a packet, the function will be invoked. So at the here is generate packet is the this is the this line represent the generation of a new packet, and the schedule time represent the repetition of that line, that at every given time this function this line will be executed. And then finally we have registered our to signal with the Omnet ++. Now this is the handle message definition of the member function handle message. Now let's see the what is handle message member function is doing. You can see that it receives an argument. It will automatically invoked by the Omnet ++ whenever this class, this simple module app simple module will receive any packet. All the code will be executed once it receives a message. You can see that the first condition, if message is generate message, you can see that generate message is here, a new message is generated, and it is scheduled, that is self message, that a module will send the message to itself, schedule at a particular interval this message. That means if 0.1 second is there, at 0.1 second a message will be generated to itself. Whenever it is generated and will be sent to itself, you can see that this condition will be true. Message will be equal to generate message. Then this line of code will be executed from there to here. What are the different line of code is used? In traffic type, you can see that traffic type is equal to 1. That means we are talking about unicast. Whenever if I want to generate any different traffic type among the 4, they may use int uniform between 1 to 4. Till in this this coding is mainly for unicast traffic, so we have made this value to be fixed. In traffic type is equal to 1. You can see that what is traffic type. This traffic type is this one. Traffic type is data type. Okay, so we are making this value to be 1. You can see here it is defined set traffic type. So for 1 it is unicast. So it means we are talking about unicast. Then we make a iterator that iterates over that map and will find that where there is a what the 1 represent. That means 1 will represent here a unicast. So EV represent is equal to cout. In C++, we in order to display any message to the terminal or to terminal, we use cout to print any message. But in Omnet++, we have to use EV, E capital, B capital. So EV, it will represent the selected traffic class type is the name of the traffic class, which it is a string type that will represent the unicast, and ENDR is for new line. Now the first condition will check. It will compare the traffic class string if it is equal to unicast. That means if condition is true, that means it will executed once the traffic class is unicast. It will compare both the string unicast with the traffic class string. If it is true, then it will it will enter in this loop in this portion, and here now since it will generate a packet, we have to send it to a random destination. So the destination is selected here in 0 to number of nodes -1. That means if we have 10 number of nodes in our network, and the address of the nodes will be from 0 to 9. It will make this 10, and from 0 to 9 it will generate any number from 0 to 9. So when a destination address is selected by this variable, Now we have to name the packet. We want to give some name to the packet, so that is stored in the pk name variable. It is an array a character variable. It will store the name of the packet. So the name of the packet is defined as follows: is print as printf is the Omnet plus plus defined member function, where what we do, we give this variable name, and it is the definition unicast packet. This is a number percentage d to, that means my address, that means from where it is generating, and this represent the destination address, and also the counter, that how much we can see that pk counter we have made it to be initialized to be 0. From here it will initialize like one. If generated packet is number counting of this generated packet is suppose that it is 10, then this value will be there. So the name of the packet will be unicast packet source address, like suppose it is 0 to destination, suppose it is 5, 0 to 5, and the number of that packet. So it will here we print this value, that generating packet and the name of the packet. Okay, now we define a new packet by making this class packet pk new packet pk name, because since we have named the packet name something, now we have to generate the packet with the same name. The generated packet, we have to, you can see that packet is a class which is defined here, packet.msg. So it is a object of that class. So now since you can see that packet message have different variables inside where we can give store the information, you can give it is defined here pk calling the member function set byte length. You can see that there is one is size. Okay, so you can give the set byte length to be the packet size, size of that packet which we have defined. It is provided as an input. Now the packet set kind from in uniform to z, this is a kind of the packet we are using. Set source address, you can see that we have defined src address here, src address, but in order to give a value, store a value, we have to do is set and get. For set we have to, it will generate a member function, a function will be generated here, member function. So to store the value, we have to use set, this will be capital S, and address. So here it is done, set address is my address, because it is source address, it is generation of address. So set my address, set destination address. You can also see that there is, we are setting this value, destination is d was the small earlier, now it is capital, destination address. You can see it was small, now it is capital, because in Omnet plus plus what we do, we start with a small letter. When it's what is completed, then we make it first letter capital, then again we make the first letter capital. Here we give the destination address selected by the from this line. Now we send the traffic class, we define the traffic class in that set traffic class. You also that there is a traffic class variable we give in store, that it is unicast, broadcast, and multicast. So here we provide the type of the traffic. Now since it is generated one packet, number of packets sent is incremented by 1, and now send, this keyword or this function is used in order to send the packet. So the name of the packet is pk, it is generated packet, and it is sent through a gate, and it is the out is a gate. You can see that this app od has a gate, out gate. This out gate is connected with the input gate of the queue routing. You can see that our network, where is it? You can see that the out gate is connected with the input gate of the routing. So this message is now defined. We have defined the different attributes of the packet, and now it is sent via this send function, member function. It is a member function defined in, as we already told, in the class simple module class. It will send the packet via this gate, out gate, name of the gate. When the packet is sent, again schedule at is used. That means schedule at it will again start a timer, that after it is sim time represent the simulation time plus the delay, that means at how much interval of packet generation. it will schedule a self message after this interval, and then a packet will be generated. You can see that there is similar statement was defined in here, generate packet. Now you can see that again schedule at, that means self message. That means when a packet is sent, now it will start a timer, and after a particular defined timer, it will generate a packet. So suppose that our generation time is 0.1 second. That means every 0.1 second a self message will come and it will generate a packet and will send. So you can say that after 0.1 second one packet is generated. That means in 1 second 10 packets will be generated. Similarly, if you make the value of here, you can see here exponential 0.01 second, that means at 0.01 second one packet is generated. That means in 1 second 100 packet is generated. So we can modify, we can define the generation rate of the packet via this statement. So now once the packet is generated, it starts again the timer, and its self message will convert. Now suppose that it may be possible that it may be possible that if this condition is not satisfied, like the traffic, because since in this case we have made it to be 1, it is possible that it is 2, because if you use into uniform 2, then generation packet type will be broadcast. So there, that this if condition will not be true, and it will go to this condition and it will be true, and execute, this statement will be executed. Since we are only talking about unicast, so we will ignore this line of code as of now. So now if both the if is not condition is not satisfied, that means if message is the incoming message, a module can receive the message from multiple simple module. So this statement is executed when it receives a self message in order to generate the packet. It may be possible that it has received some packet from a source whose destination is this defined module. So it will happen that if else, that means if any other packet is come, so what it will do, it will be check the message from check and unicast, make the message, check the form of the message to be packet form, and it will print this information, received packet, the name of the packet. You can see that packet get name will give the name of the packet, returns the pointer to the object's name, string stored in the object. This function never return null pointer. So it will give in this packet, we are extracting information from the received packet, like packet get name, what is the name of the packet, after packet get hop count. This hop count is defined in the routing module. So here you can only understand what is get hop count. You can see that set and get hop count is used for setting the hop count. You can see there is a hop one second. Okay, so you can see that there is a defined hop count. So we are retrieving the value, we are not setting the value. So what is used, get hop count. First letter was small, but here it is a capital. It is a way of giving some value to a variable defined in the packet. So this one is we get hop counts from this is a packet source at destination, get source at destination. At the early you can here we already explain you set source at destination. Now it is we are retrieving the information. So get source address to now with end-to-end delay. It is the sim time, packet generation time, it is simulation time, and the packet generation creation time. Whenever a packet is created, a time step is stuck with the packet, and whenever we want to see what is the end-to-end delay, then you can always use this line simulation time minus the creation time of the packet. It will give the value, and it will give the value. This value, this line is printed as output. Now since we have received our packet, now we want to record this value. So for this we have to use this keyword emit. Emit will emit keyword stores the end-to-end delay signal. It is our registered signal, name of the signal, and it will store this value sim time minus creation. That means when current simulation time minus when the packet was created. So the difference will give the end-to-end delay. Now another is the we want to also store or record the hop count, how much it have gone through the, what is the its hop count. So emit hop count signal, it is the name of the signal, and get hop count. Okay, and the this counter will increment by one because it has received one packet. And now since we have to done all the information, received all the information from the packet, now we will delete the packet with the keyword delete. So okay, so this is the complete detail of what are how app.nad is defined in C++ class. In C++ we have defined a new class which is called class app, which is inherited from C simple module. We have defined different private attributes, variables, public from member function and protect member function, and we have make the constructor and destructor. We have also registered this app.nad class with our Omnet++ simulator, and now we have defined two member function here. One is the initialize member function, and another is the handle message member function. Always handle message member function is automatically called when a packet is received by the module. So it is all about the app.ccc. In the next tutorial I will explain about the routing.nad already and its implementation over C++, that is routing.nad. This one, this is a heart of our implementation. It have a lot of information to be, and that is responsible for successful implementation of UMW. So for the next time, it's bye, and let's meet in the next tutorial.